Thank you very much. Thank you for the invitation. I'm very happy to be here with all of you. I'm going to talk to you about some of the work that we have been doing in the team. Where I am, this is joint work with Jedong. Fedor was an intern from EPFL. Jan Mo, Dan, Joan, Chen, and Imed, all of them from Google, and Martin Yagi, who was in Google before, but since several years ago, he's in EPFL. And I'm going to be talking in general about large language models and some experiments that we have been doing to understand how these models, which are purely statistic, can benefit from a structured knowledge graph-like information. I guess many of you know about large language models today, but I'll give a quick introduction for the ones who don't know. Large language models are based on a few very simple principles. One is transfer learning, and one of these ideas is maybe we can do unsupervised pre-training with very, very cheap ways of collecting training data. Then the hope is that this will inject some knowledge into the language models that will be helpful for downstream tasks. And the second idea is multitask training. Train a model to solve multiple tasks simultaneously. And then the hope is that there will be knowledge transfer across all of them. Like some information encoded into the model to solve some tasks will be useful to perform better on the other task. And finally, scale. Have bigger models and bigger amounts of data to train them. Regarding unsupervised pre-training, this is something that started becoming popular a few years ago, and this is a typical way in which this is done today. So you have a text, and this is taken from Wikipedia, a Wikipedia document, and you just remove from the text some words or some word spans and replace them with placeholders, and you ask the model to reproduce what was missing in that text. This is a very easy way to be able to produce a lot of training data very easily, because you just need text, that's all. And text, you have it available. It's in the web, it's in libraries, in book collections, and it's very low bar of entry access here to produce a large collection of text. And once you have this, you can scale to trillions, to trillions of words, to quadrillions of training examples using this procedure. So it's virtually unlimited, the amount of training data you have. And this is in contrast to supervised fine-tuning, or supervised training, which is what was more popular before, where you have an end task that you want to solve. It can be anything from identifying entities in text, identifying names for these entities, identifying properties like dates or locations. And in order to do this, typically, the procedure is to take some text and have it annotated by humans, produce human labels. If there are semi-automatic ways of producing these labels, then maybe you can produce silver data that is not completely accurate, but it can be helpful. But typically, you need also some human-curated data. And in this case, obviously, the size of the training data will be limited by your budget. You will have a certain budget to hire people to write these annotations, and that will limit how much data you can have. This is a very simplified chronology of how these models evolved over time. Like we could say, actual applications, product quality applications of neural networks in NLP started around 2014 with word embeddings. Word2Vec and Globe were some of the earliest examples, where they were also trained unsupervised. So these word embeddings were trained to represent the words based on the context in which they appear. And typically they were used as features for cross-attention models, for other different kind of models that didn't have to be neural models, but could be neural models. And then also during these years, 2014, 15, 16, people started use recurrent neural networks, initially RNNs and LSTMs, and so sequence learning became the state of the art at the time. And there is this example, semi-supervised sequence learning, which is one of the first examples where they propose to do this unsupervised pre-training. They produce good results, but the idea didn't really caught on yet. It needed 1.5 more years until the unsupervised sentiment neuron paper came out, where they also were doing unsupervised pre-training and showing that it led to good results on sentiment analysis. And then the field was grounded in 2018 with models like ULM-FIT, Elmo, GPT-1, on BERT, and also during this year the community transition from using recurrent neural networks, like the first couple of examples, to using transformer-based models, self-attention. And then after that, there's been a accelerated progress, I would say. And I want to highlight T5 here because it's a model on which the experiments I will be talking later are based on. And for this unsupervised pre-training, I was mentioning you need a lot of text, and text is easy to produce, but you still need some infrastructure and some time to collect the text and to clean it. And for that, for the development of T5, the T5 team at Google, they also published this dataset, the Common Crawl Web Extracted Text, also known as C4. And it is a resource that many people are using to train these kind of models. It's a very simple idea. Just take a web crawl. The first version of C4 was in English. And a few heuristics to clean the dataset. For example, removing lines that were not ending in punctuation, removing anything that looks like JavaScript, removing any complete page if it contains placeholder text or if it looks like programming code or if it contains any kind of bad words or bad content. And deduped the data to make sure, because there are many copies of web pages in the web everywhere, so some deduping there to make sure the content is it has enough variation and there are not sentences that are overly represented there. And this results in about 750 gigabytes of cleanish text that is available for download here. So once we have this data, one more example of how this works. Let's suppose that in our corpus we have a sentence like this. SwissText is an annual conference that brings together text analytic experts from industry and academia. So the first thing to do is take the sentence and randomly select one or several spans that you're going to mask out. Like, for example, could be annual conference and industry in this case. These spans are replaced with placeholders, and then you train the model to tell you for each of these placeholders what is the text that was originally. It's a very simple idea, but in order to learn to reproduce this, so on the one hand, as I was saying, it's trivial to produce trillions of words of examples of this data. On the second hand, for a model to be able to reconstruct the original text, the model needs to be able to understand how language works, to understand what is a properly grammatical sentence, and to understand what makes sense semantically. And that's why pre-training on so much data results in a very, very powerful model that we will see later some examples that there are even emerging properties that are surprising. Okay, now, how about supervised training? How is supervised training done when training these large language models? These models, we are going to stay close to how pre-training was done. And if you look at pre-training, this is a generative model. The input is text, the output is text. Once you have it training later, there is no limitation in the sense that it's an encoder model, takes the input, encodes it, and then the decoder generates the missing content for these placeholders. Once you have it training, it's flexible. You can take the encoder and you can plug in, for example, a classification head or a regression head in the output, and then you can use this model for document classification, in multi-class classification, for any kind of numeric prediction. So in that sense, there are no limitations, but for fine-tuning, for pre-training, and typically we stay close to this text-to-text mode, treating it as a generative model. And same as pre-training is done in this way, finding the content of the placeholders. The supervised multitask training is typically defined by telling the model what to do with a prompt. Telling the model what is the task that it needs to solve by providing a prompt with instructions what to do. Like in this case, if you want to train it for machine translation, you could provide a prompt like this: translate from English to German and the source sentence, and then you train the model to produce a target sentence. But there can be many different tasks that you can train simultaneously with this multitask training. So you could ask the model to distinguish which sentences are grammatical from which sentences are not grammatical. Or you could train the model to tell you a number representing the sentence similarity between two sentences. And you can look here that you can do this as a text generating model, asking the model to produce as plain text ASCII a numeric number representing this similarity. And this is how these models are pre-trained, as I was saying. Then later, if you're applying this to a different task in production settings, you can do actual classification here and predict the number more with as a real number. But this keeps all the tasks with the same format. The same input is text, output is text, and that simplifies the architecture. And this is another example. You can ask this model to summarize a text and produce a summary. And internally, all these things are based on transformers. Transformers were initially presented a few years ago with this attention is all you need paper. The advantage with respect to recurrent neural network is that recurrent neural networks consume the input sequentially, but here these layers, they can attend over the whole input simultaneously, and it makes empirically it makes them much more powerful than RNNs. So this is how the initial T5 model was produced. There is this unsupervised pre-training, which is a transformer model of the same size as BERT in the first experiments. And we take this C4 dataset, and from this C4 dataset, we produce the training examples for a mass language model. Once we have this pre-trained on the mass language model, we already have a network that is initialized with some weights that is a very powerful language model, that it has seen so much data that it understands very well what kind of content fits in every context. And then you can take this and you can do multitask training, fine-tuning this model using this prompting on all these different tasks simultaneously. And as it is being fine-tuned, every time a checkpoint is produced, the checkpoint is evaluated on a validation test set, and the checkpoint with the first results on the validation test set is chosen as the best one. And that one can then later be applied to the unseen test set and to see how well this performs. These are just some numbers about different model variants that were tried in the original T5 paper, the small base large, XL and XXL, with increasing the number of layers, increasing the number of the dimensions of the internal state. So the number of parameters ranges between 60 million for the small one to 11 billion parameters for the largest one. And these are results on using all these different sizes, small, base, large, XL, XXL, on all the tasks on which this was benchmarked. And you can see that for most of the benchmarks, when this was published, it produced state-of-the-art results for GLUE, CNN Daily Mail, Summarization Dataset, Squad, SuperGLUE. These are all benchmarks. Some of these contains many different tasks. Could range from sentence similarity to sentiment analysis or question answering. So for the first 4 datasets, the largest size of the T5 model produces state-of-the-art results on all of these benchmarks. It didn't produce a state-of-the-art result on machine translation, but it got very, very close to the state-of-the-art results, which were traditional machine translation systems that had been trained on high-quality parallel corpora and were models that had been specifically designed for machine translation. So overall, this looked very, very promising. And I want to show you some examples. These examples, I got them last week, taking one of these T5 models that we had trained internally on our own data sets and testing them and see what happens. And I was saying that there are these emerging properties of this model from having seen so much data. The first example, I just take one of these fables from Aesop, the shepherd boy and the wolf. I think it will be familiar to many of you, this shepherd who says, a wolf is coming, come to help, and all the villagers come and help, and then he laughs at them, it was a joke. Several times, finally, when the wolf comes, no one goes to help because everyone assumes it's a joke again. And I asked the model, the moral of the story is, and I put a placeholder, and I asked the language model to fill what was missing there. And the language model writes, do not play tricks on those who would help you in a time of need, which is a really great moral for this story. And it's not in the input, it's figured out, that fits in that context. Another example is the summarization example. I searched in Google News, I took a news document, one more of these studies that says that coffee helps you live longer. That's good news. So I asked in the end, what's a summary for this story? And the model produced coffee consumption is associated with reduced risk of death, which is a pretty good summary. It follows closely the second sentence of the article, but still it's good that the model decided to focus on that sentence, which is the most important one, and it's a little bit paraphrased to make it more standalone. This is also another example where I fed the model this is a made-up story. John found 3 strawberries. He gave one to Jane, one to Peter. Jane gave her strawberry to Peter. At the end, John has X, Jane has Y, and Peter has Z. And the model outputs X is 1 strawberry, Y is known, and Z should be 2 strawberries. And this is actually a correct output for the input I provided. These models are hand-selected. Okay, so I played a little bit with the system. I chose the models where the model did right. These models are not trained to do arithmetic, so same as this example worked. I tried a few other examples that didn't work. But still, the fact that sometimes it gets it right, I find it pretty amazing. That just based on this fill-in-the-blank objective, pre-training, sometimes it learns to do some arithmetic, or at least it learns that 1 strawberry probabilistically is the most likely filler for X given the previous context. It's also possible to use these models in what is called few-shot learning. In few-shot learning, you provide a few examples of the tasks you want them to solve, and then you provide the real inputs that you need the classification for. Like in this example, I tried to write, I really enjoyed this movie, it's a positive review. I walked out of the cinema, it's a negative review. And then I asked the model, how about the next 2? The plot keeps you on your toes throughout the movie, what is it? And it should get the prize for the most boring movie, what should it? And again, it makes it right. It decides the third one is positive and the fourth one is negative. In this case, this is the first example I tried for something like this. I didn't really engineer it, and I tried to use metaphors, things that were not obvious, like walked out of the cinema or keep you on your toes, or the last one mentioned a price. A price tends to be positive, but in this case for boring. So it does it right. Now, the last 2 examples I want to motivate the next section of the talk. These models can also memorize facts. And if I take this T5 model and I asked it, the movie Jaws was directed by X in Y, it filled in the X is Steven Spielberg and Y is 1975, which is correct. So it means it's learned that fact from the pre-training data. It's pre-trained on the web. The web contains, for example, the Wikipedia article for JAWS or the IMDb article for the IMDb page for JAWS. This information is encoded there. So from the pre-training data, most likely, the model has already seen maybe several times this fact and has memorized it. And if I ask the model to fill in these blanks, it can give you the right facts, which is great. But then I tried another example. City Lights was directed by X and Y, and then in this case it output wrong data. So the director was Charlie Chaplin, and it said it was John Ford. The year was 31, it said 32. It was close, but not quite right. And one of the problems of these models is that they are trained with this language model objective that are so powerful that they produce very plausible fillers. If it's an older movie, okay, John Ford directed all the movies around maybe in the 40s, 50s, the year is close, so they produce an output, but it's not so easy to know when it knows the fact versus it's hallucinated something plausible. It's very different, very difficult to distinguish this. And if you want to apply this model, say for a search assistant or for a conversational interface, they tend to give you sometimes correct answers, but sometimes they give you the wrong answers, but stated with so much confidence and stated so grammatically correct that they're actually very misleading when they're wrong. And then another example is that this, what we call multi-hop reasoning. If you ask something like other movies directed by the director of Schindler's List are this and this is not a direct fact with a subject, predicate, object. You need to do several hops in a knowledge graph. You need to know, given this movie, this is the director, given that director, he directed these other movies. This kind of mass language model objective does not train the model to do this kind of chain reasoning, and it tends to fail always with this kind of context. So I'm going to talk a little bit about some studies that we did on memorization. And we're going to be focusing on question answering. Question answering, we can handle it academically. We can formulate it in 3 different ways. The first way would be reading comprehension, and this task is defined. You have a question, you provide some context. The task of the model is to understand this context and provide an answer based on that is supported by that context. Like in this example, what color is a lemon? The context is telling you that the lemon is a yellow, so this answer can be extracted from the context. A slightly more different problem is when you don't provide the context. The user does not provide the context. The user just provides the question, but you train the model to do some kind of retrieval augmentation. The model receives a question, and it can encode the question. It can use some procedure to do retrieval from a database. The database can contain facts or passages or embedding vectors from encoded passages, for example. And then based on the retrieved passages and the question, the model needs to extract the answer. So there is one more step here that the model needs to learn, which is given the question or the encoding of the question, how to retrieve relevant passages. And the third one is closed book question answering. When you just provide the question, there is no retrieval augmentation, and the model needs to produce the answer. And this can only happen properly if the model has memorized the answer during pre-training. In the T5 paper, actually, they also explore this a little bit, and these are some examples. In the training data, you have different sentences, and some of them may contain a certain fact, like may contain that a given person was born on a given date. And then if you ask T5 in the closed book question answering setup, you ask the question, you expect the model to produce the answer. They tested this out on several open domain, on several data sets, natural questions, web questions, and trivial QA. And they found that it doesn't perform too badly, but it doesn't get close to the open domain state of the art. It's significantly underperforming even the larger T5 models. So one thing that they tried as an improvement is what is called salient span masking. In the example I presented at the beginning of the talk, I said that the spans that are removed with this unsupervised pre-trained objective, they were random, but they don't have to be. You could use, for example, in salient span masking, you want the model to memorize a fact, so then you go and you mask out exactly what you want the model to memorize. In this example, this is the first sentence also of the Wikipedia page about the movie Vertigo. If we want the model to memorize the release year and the director, we can go straight and mask specifically those two spans and ask the model to produce, during pre-training, to produce them. And this can be done on a large corpus, same as before. And if you compare T5, if you take a T5 checkpoint and you add either continue pre-training on the C4 dataset with random masking, or you continue pre-training on the C4 dataset but using salient span masking for the relationships that you care about, you can see that the random masking has reached a plateau. Additional training does not improve the exact match score on the predicted answers. But using salient span masking, it keeps going up. It keeps improving. The model is learning the facts that will allow it to produce the right answer to the questions in these data sets. And now if you expand XXL with salient span masking and you evaluate on these data sets, you see there is a big improvement on all three of them. And in web questions in particular, it became the state of the art, T5 with this masking approach. So, wrapping up a little bit, there are two ways in which we can leverage structured knowledge graph data for question answering. The explicit approach would be, for example, this retrieval augmentation. You train the model to query your knowledge graph. And this query can happen in different ways. I've seen papers where people train the language model to produce a structured query for a knowledge graph. It could be SparkQL or something like that to actually produce a query that then is executed over the database, retrieve the answers, and then extend the input with the test representation of these answers. And then the model do a second pass over that and produces the answer. And a different approach is more embedding based. You encode the query, you encode the potential answers, and you look for closeness in the embedding space, and then you retrieve the potential answers that are the closest to the encoding of the question. So there are many different ways, but all of them have in common that they're explicitly querying a knowledge graph. And the advantage this has is that you can access the whole knowledge of the KG. The other approach, which is memorizing facts inside your model, has the disadvantage that it's not guaranteed to remember the whole KG. You can use salient span masking, you can provide all the facts in your knowledge graph, but this is a black box. You don't know how much is remembering from it, how much is memorizing. So the explicit retrieval from the KG is interpretable, but the implicit one is a black box, I was saying, it's not interpretable. The explicit retrieval requires, but on the other hand, the explicit retrieval requires different architectures and is harder to productionize. Requires to store the knowledge graph for inference and requires to have different neural architectures that allow the model, for example, to do two passes, to do first the retrieval stage and then do a second stage. So it's typically different architectures. Sometimes you need to combine an embedding tower with a cross-attention model to produce the answer. So it's more complicated setups. In the case of memorization, you just have your model, your transformer model, that is your language model, and it will learn inside the same model. In the weights will codify the facts that you wanted to memorize, to remember. And the explicit approach is something built ad hoc for this question answering setup or setups where you need more grounding. The implicit approach, as we saw, T5 is very generic. It can be applied to many different tasks. Some of them may require knowledge, some of them may not require explicit knowledge. You just have one model that can solve all of them because it was trained for multitask setup. And basically, and as I was saying, you just have one T5 model. One T5 model that additionally has memorized additional facts in the implicit approach. So you can easily replace one model with another model without additional complications in production. So we're going to look at these two in the talk, but we're going to start looking at the implicit memorization. And I will talk about some experiments that we did. They are not close to having production applications, but we wanted to understand better how this works internally, and if we can draw some conclusions about it and best ways to train these models. We call it knowledge infusion, this memorization. And the idea is we have a knowledge triple, and the triple always have a subject, a predicate, and an object. And we can do two things to feed it into the large language model. One way is, the obvious thing is to dump the triple as a string. If we have a human readable name for the predicate, we can just give the name of the subject entity, the predicate name, and the object name. This is easy to obtain. But one question we had is, this is not natural language. And we had seen, there are papers like Ernie and Kelm that tried already to provide structured information to the large language models, and typically what they do, because these LLMs are always traditionally trained on natural language models, what these papers try to do is to align structured triples with natural language sentences. But this requires additional machinery. You need to be able to either generate sentences based on the triples or align the triples to sentences in some way. You need this triple to text mapping in order to put your knowledge graph in a format that can be consumed by natural language, large language models. So we had this question: what happens if we try just passing the structured knowledge, just dumped as a string much more easily? And the task is the following. We wanted to memorize, for example, the objects or the subjects or the predicate names. So in this example, we mask out the object. In the first example, directly from the triple. In the case of natural language, from inside of the sentence. And the target is the same in both cases, the name of the object. We used as a starting point some previous work, which is the Kelm dataset. What the Kelm authors did was to take Wikipedia and Wikidata and align the Wikidata triples to Wikipedia sentences. For a Wikidata triple, find a sentence in Wikipedia that mentions explicitly the subject and the object, and some additional cleaning of the dataset to remove the false matches. And then they train a T5 model. But the problem with this alignment is that it will not have full coverage. You will not have sentences on Wikipedia for every single Wikidata triple. So in order to have full coverage on your knowledge graph, they train a generative T5 model to consume a triple and generate a sentence using this alignment as training data. And once they had this model, they ran this model over the whole of Wikidata, and for each triple generated a sentence. And now you have a natural language sentence that represents each of the Wikidata triples. So, in that way, we use the Kelm dataset to have this alignment between the structured triples and natural language sentences, but we also used the directly dumping the triples, subject, comma, predicate, comma, object, without natural language sentences. And we validated this on closed book question answering tasks. You have a question like, for example, which city is capital of Germany? And this requires external knowledge for answer. So the data set we tried, previous QA, WikiHop, Trivia QA, and natural questions. Then Wikidata has 35 million triples, so you get an idea of the scale. And Kelm has 15 million sentences. So they don't actually have sentences for every single Wikidata triple, but they have okay coverage, acceptable coverage. And this is important while training. We did a mixture with the C4 corpus, with random masking, because if we take T5 and we just fine tune on this Wikidata data set, we observe that the model forgets the previous pre-training and replaces previous knowledge with just this structured information we're providing now. But by mixing this structured knowledge with the original pre-training, we ensure that it keeps remembering what it had been pre-trained for to begin with. So we do number of training steps between 100,000 to 500,000, and these are some results on these two datasets, FreeBSQA and WikiHop. And what we were happy to learn here, first of all, there is some improvement versus the vanilla T5 models. The second line is the vanilla T5 model with additional pre-training using the C4 corpus. And the reason we did that is that we want to make sure that the improvements are due to the structured data. They are not due simply because these models will have been trained for a bigger number of steps. So by doing additional pre-training with the original C4 corpus, we make sure that in number of steps is comparable, and we have one fewer variable to consider here. And you can see that on these two data sets, knowledge injection provides better results than using original T5 on all the metrics. And something that we were happy to see is that numbers are pretty comparable between using the dumped triples versus using the natural language scale sentences. And what this is telling us is that we don't need all this additional machinery of aligning triples to sentences, training the generative model, and producing the sentences for the triples. We just can dump them very easily, and this is a much more scalable way of having a large large knowledge graph and dumping it in a way that the language model can benefit from. So this was the first conclusion here. If you look at the other two datasets, Trivia QA and Natural Questions, what we saw here is that the improvements are much more modest compared to the vanilla T5 models. And looking more into these datasets, we found that actually they contain a lot of questions where the answer is not expected to be in Wikidata. Some of them are, for example, which person said this quote. Wikidata doesn't contain quotes. Many questions refer to facts that are not even modeled by the Wikidata schema, or even if they are modeled, the fact does not exist on Wikidata. And therefore, simply because the fine-tuning data and the test set are not really aligned, so we didn't see big improvements. So what we did also as a proof of concept is to say what happens if we take these two data sets and we filter the test examples with a very simple criteria. We keep only the questions that mention an entity that is either subject or object of some triple on Wikidata. And in that case, we know that the question is talking about something that Wikidata knows something about it. It's still not guaranteed that Wikidata will have the answer to that question, but we get rid of a lot of questions that we know for sure Wikidata will not have the answer for that, because if they only mention entities that Wikidata has no fact for them, then we know for sure the answer is not in Wikidata. And if we look at this subset of these two data sets, now we see that the improvement is there and is statistically significant on all these cases. And for all the sizes of T5, now we can measure some improvement, which is good news because it means the model is memorizing the information that we want. And finally, also as a proof of concept, we verify that in a data set that doesn't require this memorization, like the SuperLU benchmarks, there is no degradation. We also want the model to to be as generic, as general purpose as the vanilla T5, and we verify this. And this was not this should not happen if we only fine-tune on the structure knowledge. But because we have this mixture with the C4 corpus while fine-tuning, that's what guarantees that it's not forgetting the previous pre-training and we have no degradation on these tasks. You can also see that the improvement over the vanilla T5 model is increasing actually already with the size of the model. Okay, so I'm going to move on to the second part of the talk, which is the more explicit retrieval. And as I said before, this can be done in many different ways, but we look here at one very concrete one. And we look at dual encoders. Dual encoders have been used for many different tasks. The idea is that you want to align two corpora. You want to align two sets of items. And for example, you may want to align images with captions, or you may want to align documents with queries for which the document is relevant. And there are different ways of training the dual encoders, but we are going to look concretely here at two specific architectures. One is use asymmetric dual encoder and the other Siamese dual encoder. In the asymmetric dual encoder, we have two encoding towers, and in the specific case of question answering, we use one to encode the question and the other one to encode the answer. And this is an example. We have a QA dataset, a closed book QA dataset. And let's suppose this is an item in this test set. Who's the wife of Barack Obama as the question, and Michelle Obama is the expected answer. The question would be passed over the question embedding tower, and this tower outputs an embedding vector. And the answer is fed into the answer embedding tower, which also outputs an embedding vector. And for training, the loss we use is the distance between these two vectors, because we want the question and its answer to be positive examples to be mapped close in the embedding space. And we also use negative examples, taking the question and wrong answers that are sampled from the same batch, from other examples in the same batch. And we train these two towers to make sure the negative examples are pushed away from each other in the embedding space. The second alternative, we could use a Siamese dual encoder. This is not always possible because sometimes you have two different corpora in the two towers. Let's suppose you're aligning images with captions. For the images, you will need an image encoder, like a visual transformer, for example, where for captions, that's text as input, you will need a text encoder. If you need different architectures for the two towers, they cannot share the parameters. But in this case in particular, the question and the answer, they are both short strings, plain text. So potentially we could use exactly the same parameters for the two towers, and that is what is called the Siamese dual encoder. And then we try this on several question answering data sets. And we observe, and for here we use T5 also. So the two encoding towers are initialized as T5, and then they're fine-tuned on these positive and negative examples for the dual encoder. And as you can see here, we got significantly better results on using the Siamese dual encoder, using the same encoder for both of them. So we wanted to understand why and what is happening here. And we tried three hybrid approaches between the Siamese and the asymmetric encoders. In the first one, we force them to be asymmetric but with shared token embeddings, so they have something in common. In the second one, we froze the token embeddings to the T5 ones. And in the third one, we went to the other side of the tower and we forced them to share the parameters for the projection layer, the layer at the very top. And we compared these three hybrid alternatives. And what we saw is that sharing embeddings doesn't really help. The performance is very, very similar to asymmetric dual encoder, but sharing the projection layer makes the asymmetric dual encoder perform as well as the symmetric dual encoder. They're pretty much undistinguishable. So let's see, and this is the Siamese dual encoder improvement over the asymmetric dual encoder on mean reciprocal rank. And you can see that for the different data sets, the Siamese dual encoder, the increase in performance versus the asymmetric dual encoder is very similar to the asymmetric dual encoder with the shared projection layer. So they're basically performing the same. And the improvement becomes bigger the larger the model is. This is also something interesting to see. With T5 large, it's much bigger improvement by being symmetric. So then we tried plotting the embeddings for both questions and answers on a two-dimensional space. And this image makes it pretty obvious what is happening here. In the asymmetric dual encoder, when you have two separate towers with different parameters, each of the two towers is projecting the input to different regions in the space. And yes, it's trained to force that the question and the answer are as close as possible, but because they don't share any parameters, each tower just choosing one region in the space and plots the things into there. And all the questions come in this place, all the answers come in this place. The Siamese dual encoder is basically projecting everything in the same region, in the same space. And there is much more flexible to ensure that the question and an answer are very close together. Now, if you look what happened with the hybrid models, sharing the projection layer has exactly the same effect that we had with the Siamese dual encoder. Everything is projected into the same space because the layer is the one at the top, the one producing the final embeddings and has that ability. Sharing the embeddings is not really helping because they're at the beginning and then the rest of the towers are completely separate. And one advantage here is that sometimes you cannot use a Siamese dual encoder, as I was saying at the beginning. If your two are very different types of data, like images and text or video and text, then you cannot use a Siamese dual encoder. They are different architectures. But you can have two asymmetric embedding towers. As long as you share the projection layer on top, you can force the two towers to have this effect, to be projecting things into the same space. So just to conclude, I gave an introduction to large language models, and they represent current state of the art for closed book question answering. And we did some explanations that try to shed some light on limitation of possibilities and current approaches, specifically looking into memorization of knowledge and looking into more embedding-based retrieval models for solving these tasks. And some of the conclusions, I just wrapping up, is we saw that for infusing data into the network, we don't really need to go through natural language. We can just dump the triples as they are, and it works pretty well. The larger models benefit more from knowledge infusion. I skipped very quickly through it, but we also did experiments with the smaller knowledge graphs. All of this is very intuitive, but it's good to test it empirically. The smaller the knowledge graph, the better the memorization and the better the improvement. Like we tried with a movie-specific knowledge graph with 100,000 facts and a movie QA data set. And there the accuracy went from like 20% to 75%, the accuracy of the answers. So basically it's memorizing a lot of the knowledge graph and it's actually being able to apply it. In the case of Wikidata, much bigger knowledge graph, you need much bigger networks to memorize it, and even the large T5 models are struggling to memorize knowledge graphs as large as Wikidata. And looking into the retrieval models, one of the conclusions we got is that sharing projection layers enables asymmetric dual encoders to perform competitively with the Siamese ones, and we recommend to use this shared projection layer in this kind of setup. Thank you, everyone.
Thank you, Enrique, for the brilliant presentation and is bringing to us this bleeding edge of research at Google. So I'm sure there will be a lot of questions now from the public. Yes.
Hi, thanks for the great talk. Very interesting. I have two questions. But before I go there, I have to draw a big picture because I'm questioning a bit the status quo. Where will it go in the future? Because now we are in a connected world. We just increase ever the data size and the model size, which you just mentioned, what you show with the common crawl C4. It's having some knowledge, but it's missing the knowledge. So it's great what you're doing, that you're adding the knowledge graph knowledge, let's say, to get more efficient, but it's still not there where we should go. And now currently there's some, it's in a bit in the space where the current AI research is in general, that with the ever-increasing data, ever-increasing models, big companies like Google or all the other big companies can do state-of-the-art research, but here small startups and small companies are a bit left out of current research, so it's actually killing some innovation, and not to mention the costs in general, computational costs, but also the carbon footprint, which is also actually a bigger problem. So now in this connectionist world, we have the sequence-to-sequence models and the transformers with the attention-based query Q value, positional encoding, mask language modeling, next sentence, whatever prediction. It's doing this sequence-to-sequence mapping perfectly, but it's still a bit blind, let's say, because it's somewhat missing the let's say, neurosymbolic AI knowledge, the semantic knowledge of it, because when I look at it, because it's trained on the unstructured text, and so this is actually a bit redundant in my sense. Why not actually removing stop and fill words or doing some named entity recognition and part of speech tagging, so you're reducing actually the amount of computational power you need to model all that. And that's actually nice what you're doing with the knowledge graphs, that you actually having a bit more condensed knowledge, letting the language model learn all those facts. And so I thought, can you do a new transformer-based attention model, which is then getting more into efficiency to avoid the ever bigger carbon footprints? And then also with the knowledge graphs, what you're showing at the moment, you do explicit or implicit fusion into the language model. Can't you do a new generation of language models, which is just based on the knowledge graph? Because there you have the symbolic knowledge, and then you can actually scale up over the whole knowledge of the whole world. So you're way more efficient, and then also then maybe such models can be used at a small startup or research university. And so I hope the answer is somewhat yes, that Google is going to neurosymbolic AI and getting more efficient.
Maybe we should let the speaker answer.
I'm soon finished. So I hope the answer is yes, because the ending the joke with maybe, I hope not that Larry and Sergey invented the company Google, referring to the number Gogol, which is a very big number. So actually to store the whole knowledge of the whole world in language model, I hope not we're ending up with a Gogol number of parameters.
Yes, you bring up very interesting topics here, and I'll cover 2 or 3 of them. One, I have a much more optimistic view about big companies and smaller companies now, because if you look at it, anyone can take today a T5 checkpoint and run it or fine-tune it. And the fact, one of the advantages of these models is that they have been pre-trained on so much amount of data, they have so much knowledge encoded inside of this checkpoint, that for tasks that before you needed a lot of training examples to fine-tune, now you can annotate with humans a much more smaller data set, 1,000 examples, sometimes not even that. Sometimes you can use few shots and just show to the model 2 or 3 examples, and then the model is able to do a relatively good job out of that. And in this way, I feel that large language models are becoming a commodity. You don't have to have a PhD on the topic to be able to use a large language model. Anyone can go to GitHub, can download the T5 checkpoint, and can start playing with it, and can build product applications out of this that a few years ago were science fiction. So I feel that the entry bar is actually going down with all of this.
I think we should give the opportunity to Atta to ask questions. If you want, you can ask the question later.
Okay. It would be somewhat related to my current... sorry. would be somewhat related, because then data-centric AI, now we had the modeling. Can you construct a knowledge graph based on my current data, but then the knowledge graph is growing on my data, and then you realize, let's say, sentence similarity, oh, actually 20, 30% of my data is obsolete because I already learned this, and so the knowledge graph is showing me the ways to perfectly construct a balanced data set, and you reject 30%, and then you know, extrapolation, I need to add some other parts to have a perfect data set.
Yeah, there are many research directions actually related to the topics you have mentioned. Like, for example, you mentioned carbon footprint as well, and consumption, and indeed, I'm not so familiar with side of the work, but between dedicated hardware, for example, is one line of work that tries to reduce the energy consumption for training these models. Other lines of work are more sparse networks that the transformer, not all layers are fully connected, by looking into ways to make them much more sparse, reducing the parameters, and then speeding up training data. All of these are active lines of research, how to make all of this more efficient and less energy greedy. And another interesting topic that you raise is this memorization versus relying on knowledge graph. And indeed, I think that relying on explicit knowledge graph has many advantages versus memorization. And the model has to do a very, very different task when it's doing retrieval versus when it's memorizing. When it's memorizing, you're expecting to have a huge network that has enough capacity that encode everything inside in the weights. But when you're doing retrieval, it's a completely different task to perform, and much smaller models can do better there, because the task is given this input, how to produce a query or an encoding to retrieve the right answers, and then the answers will contain the content I need to reason over these answers to produce the output. And you need much smaller capacity for that, smaller networks, so it changes the paradigm a lot. I think there was another question.
Yes, thanks also from my side for the nice talk. My question was concerning these examples where the model was giving confident but wrong answers. Are there any attempts using these knowledge graph techniques to incorporate uncertainty, to maybe, I don't know, say, I don't know, but my best guess is John Ford?
There are different approaches for that, but I think it's a very active research area, so it's not at all a solved problem. One way to improve grounding is precisely through this retrieval augmentation. So you could have the language model actually issuing a search to a search engine, or issuing a request to a knowledge graph, and then retrieving the answers, and that is proven to increase the accuracy of the answers a lot. So I think most of the research work I've seen about it has been about increasing the accuracy by grounding into some trustable data set. Not so much about producing a confidence, because I think that's not so well understood, how to get these models to produce a confidence, because the answer might not be very confident because of language modeling problems with the answer, or because of factuality of the answer, and it's difficult to distinguish these cases.
Thanks.
I think there was previously one here.
Hi, thank you for the nice talk. I have two questions, one like a little bit specific and one general. So the specific question would be how these models can handle like negations or valence shiftings in general, like for example, for sentiment analysis. You are doing some research in that area. And the general question would be, how would we construct like a knowledge graph in an unsupervised approach, like from the text, specifically how the edges can be labeled in a generalizable way, or to generate the triplets from sentence, the reverse process. Thank you.
So the pre-training is already capturing metaphors and negations and many other linguistic phenomena, simply based on the size of the model and the size of the corpora it has seen. If you have a specific application you want to apply this model to, say for example review sentiment analysis, typically what you will do is to first take a vanilla a large language model and run it as 0-shot or few shot and see how well it does. And you may be surprised, and it already performs well enough to meet your quality bar that you were expecting. And if that happens, it's great. If that doesn't happen, and there is a specific pattern of inputs that the model is not performing well on, typically people do active learning at that point. So collection of human annotated data that the model is making mistakes or is close to the decision boundary, and there are hard positives, hard negatives, and then fine-tune the model on this. So like a standard machine learning approaches applied to LLMs are applicable to LLMs as well. About inferring the KG from the LLM, sounds like a very exciting task that I personally I have not worked on that in Google. But it sounds like a very exciting task to formulate as a text-to-text problem and try to see how well it does. Yes.
Thank you.
So, yeah, thank you very much for your talk. So I have to admit, I'm one of those people who treats these models more like a commodity. So I have a question a bit about the training procedure. So I remember a couple of years ago when you had like these massively multitask models, like they would all kind of suffer from this catastrophic forgetting problem. And here it seems like it's basically a solved problem now. So can you maybe give us an intuition, like how you deal with that during, if it's the training procedure, if it's just the size of the model, like what happened?
Oh, forgetting does happen. We've seen it happen in these large language models, and it's very typical. You get a T5 checkpoint, and the vanilla checkpoint may be applied to a certain task, and it does very well, and then you fine-tune it on your fine-tuning data, and it overfits your fine-tuning data basically, and it forgets a lot of things that it had learned during pre-training, and then you see when applying to unseen data, sometimes the vanilla model does better than the fine-tuned model if this has happened. So it's something that we see in practice. The typical approach there is to be very careful about the mixing proportions when you're fine-tuning. If you see some kind of forgetting happening, you include a mixture with the data that you see the model forgetting, and it's a bit of cooking also to trial and error to decide what is the right mixture proportions here.
Okay, thank you very much.
Sure.
Hi. Another question. You mentioned that these models can be considered as commodities, and they are lowering the entry bar and everything. But then it has been shown that these models can have a lot of bias, and there is a lot of underrepresented population communities, and also underrepresented way of conceptualizing the things. So we need to kind of believe that these big companies are doing their proper work to handle this, and on how are you tackling this kind of problem?
Yeah, so whenever we take these language models and we want to apply it to production, Google has by now some pretty big teams about fairness in artificial intelligence and inclusion, and typically these are experts on these things, and then they have specific data sets and they have expertise with that. And typically when you want to bring something like this into production, is you have to schedule office hours with these teams, you have to explain how you have trained them, how you have to apply them, and often they ask you to run it in some of their data sets, or even to construct a new data set specific for your task, having this in mind. So indeed, it's a very important topic. And within the company, we have processes in place to catch as many as possible of these potential biases before a model like this is actually integrated in a real application.
All right, so thanks. If there are no other pressing questions, we finish here. We conclude with a little present from the organizer for our speaker. So Enrique, thank you very much for being with us today, for bringing us the knowledge Google. Now, a bit of information. We have the coffee break outside, and after the coffee break, in 25 minutes, we'll start again here with the business application session, and upstairs with the junior track session 1. Enjoy the coffee break.